Welcome to Submodule 3 of 4 Terminology and Directional Calculations. In this section, we are going to cover the rectangular and polar coordinate systems, then demonstrate how to transform quadrant and azimuth readings. So let's begin. Let's now look at the compass quadrant method, a foundational concept in directional drilling used to describe the azimuthal direction of the wellbore. Looking at the picture on the right, in this method, the compass is divided into 4 main quadrants: northeast, southeast, southwest, and northwest. This system is often used early in the well, especially during kickoff from vertical, where it's important to orient the bit in the right direction using a tool face display. Unlike the azimuth system, which measures a continuous 0 degrees to 360 degrees around the compass, the quadrant method breaks it down. Angles are measured starting from either the north or south axis and then expressed with a direction toward the east or west. For example, a bearing of south 30 degrees east means 30 degrees east of due south, which is equivalent to an azimuth of 150 degrees, which is shown in the left picture. This convention makes it easier for drillers and directional engineers to quickly interpret the bit's orientation, especially when working with surface or near-bit sensors. It's particularly intuitive when visualizing tool face positions in real time while steering. In the field, accurate interpretation of these quadrant readings is essential. Misreading tool face orientation can lead to steering in the wrong direction, potentially increasing dogleg severity, compromising wellbore stability, or even missing the target reservoir. Understanding and using the compass quadrant method correctly ensures smoother directional control, more efficient drilling, and ultimately better reservoir access. Okay, question. When would I use a quadrant reading when I am drilling? I will give you a moment to think. The quadrant reading is used by the directional driller for his tool face display when kicking off from vertical. A tool face display is shown on a monitor in the doghouse, where the MWD tool sends up continuous readings showing its azimuth. The directional driller uses this to steer in the right direction from vertical. This is the process done when steering with a mud motor. Let's now focus on azimuth direction, used in directional drilling to define the path of a wellbore in the horizontal plane. This means on a 2D plot looking at the plan view. In the azimuth system, directions are measured in degrees from 0 degrees to 360 degrees, with all readings taken clockwise from true north. So 0 degrees or 360 degrees indicates due north, 90 degrees is due east, 180 degrees is due south, and 270 degrees is due west. This system provides a continuous, unambiguous bearing reference, which makes it ideal for describing wellbore trajectories as they deviate from vertical. The slide shows an example, an azimuth of 150 degrees, which lies in the southeast direction. This is equivalent to a quadrant bearing of south 30 degrees east, meaning 30 degrees east of due south. Azimuth is used extensively in well planning, geosteering, and real-time trajectory control. For instance, once a driller begins to steer away from vertical during a kickoff, the bit's azimuth becomes critical for hitting directional targets, avoiding collisions with nearby wells, and optimizing the wellbore path for reservoir exposure. Modern measurement while drilling MWD tools and rotary steerable systems provide real-time azimuth readings, allowing for continuous course correction. Errors in azimuth interpretation, even by a few degrees, can translate into significant positional errors at depth, especially in long horizontal wells. That's why azimuth accuracy is vital for wellbore placement, collision avoidance, and reservoir contact, ultimately impacting the productivity and safety of the entire drilling operation. So, question. I am on an azimuth bearing of 80 degrees on the compass. What would my quadrant reading be? I will give you a moment to think on it. The answer is east 10 degrees north. The reason for this is that we have gone over 45 degrees, so the easting dominates the reading and is pronounced first. Now let's walk through a short exercise that will help reinforce your understanding of quadrant and azimuth directions, which are both vital for directional drilling. The first part asks us to convert from quadrant to azimuth. Let's take the first example, south 23 degrees east. This means we're starting from due south 180 degrees and moving 23 degrees toward the east. So the azimuth would be 180 degrees minus 23 degrees, which equals 157 degrees on the compass. Similarly, for north 14 degrees west, you start from due north 0 degrees and move 14 degrees toward the west, which gives you an azimuth of 360 degrees minus 14 degrees, which equals 346 degrees. These conversions help us translate intuitive directional terms into precise numerical bearings, which drilling software and tools rely on. Please stop the video and try questions 3 and 4. Okay, how did you do? I am sure you smashed it. If not, go back and look at it again. In the second part of the exercise, we do the reverse, converting from azimuth to quadrant. Let's look at 214 degrees azimuth. Since this lies between 180 degrees and 270 degrees, we're in the southwest quadrant. Subtracting 180 degrees from 214 degrees gives us 34 degrees, so we write that as south 34 degrees west. Now stop the video and have a go at questions 2 to 4, and let's see how you do. Okay, here are the answers. Understanding this conversion is key when working between surface displays, downhole sensors, and reporting systems. Toolface readings and surveys may be given in quadrant format at the rig site, while most planning software operates in azimuth. That's why being able to quickly move between the two systems is critical for real-time decision-making. This exercise mirrors what field personnel and directional drillers must do frequently: interpret directional data quickly and accurately. It's not just about theory, it's about ensuring the bit is going where it should, hitting the target zone, and avoiding costly mistakes. Now, let's move on to polar coordinates and rectangular coordinates. Polar and rectangular coordinates, two essential systems for defining wellbore positions in directional drilling and well planning. Polar coordinates define a location based on two components, a distance and a direction from a fixed reference point, typically the surface location or another well. In the example shown, the wellbore's position is represented as 2,572.68 feet at an azimuth of 217.72 degrees. This means the point lies that distance away, oriented along a bearing of 217.72 degrees, which places it in the southwest quadrant. In contrast, rectangular coordinates, sometimes called Cartesian coordinates, define location using north-south and east-west offsets from the reference point. These are typically measured in feet or meters and provide a more intuitive way of plotting well positions on a map or grid. Both systems are widely used in the industry, but for different purposes. Polar coordinates are especially valuable in target planning, for example, when defining the trajectory to a geological feature like a fault or a reservoir sweet spot. It allows engineers to visualize the well path in terms of both direction and range. Rectangular coordinates are typically used for surface plotting, collision avoidance, and spacing calculations, as they simplify the measurement of distances between wells and infrastructure. While older practices sometimes used quadrant bearings with polar coordinates, the industry has largely shifted to using azimuth for consistency and accuracy, particularly with modern software. Understanding how to interpret and switch between these systems is critical for well planners and directional drillers to ensure precise well placement, efficient trajectory execution, and safe field development. Okay, question. If my polar coordinate was 2,000 feet at 0 degrees azimuth, what would my northing and easting coordinates? I will give you a moment to think. Well, I have travelled due north, so I have not moved east or west. Therefore, my northing will be 2,000 feet, and my easting will be 0. Okay, now let's look at an example. If you remember back to high school, in trigonometry, we used a simple acronym, SOHCAHTOA, to remind us of the relationship between sides and angles of a right-angled triangle. When looking away from the corner of a triangle, the sine of an angle is the opposite length divided by the hypotenuse length. The hypotenuse is the longest side of a triangle. The cosine is the adjacent divided by the hypotenuse, and the tan is the opposite divided by the adjacent. Here we wish to drill a well from our well reference of 0, 0 to a target location 1,450 metres to the south and 1,250 metres to the west of the surface location. We can use Pythagoras' theorem. Looking at a triangle with corners A, B and C, the theorem states that the square of the hypotenuse length AC is equal to the square of AB plus the square of BC. So if we know two lengths, we can calculate the length of the third. In the example, to calculate the length of AC instead of the square of AC, we need to square root of the other side of the equation. In this case, the length of AC is 1,812.5 feet. The next question is, in what direction do we need to travel to hit the target? In this example, we are given the length of AB and the length of BC. So we can calculate the angle theta as tan theta equals BC divided by AB, which gives me 0.862. There, converting this to degrees, I apply tan to the -1 to 0.862 to provide me with 40.8 degrees. This is a quadrant reading of south 40.8 degrees west. Converting to an azimuth reading, I need to add it to 180 degrees to give me 220.76 degrees azimuth. Okay, let's recap. In this section, we worked through how to do conversions between rectangular and polar coordinates. We then worked through how to transform quadrant measurements into azimuth readings. In the next section, we will look at doglegs and demonstrate how to plot surveys. Now, please do the associated quiz, and I will see you in the next section. Thanks you,